other questions with that? So I can go back. Technology. All right, so really, redox reactions should have been something that you learned in Chem 1. And I don't even know if my Chem 1 students, if we even got to it or not. But now we're going to start looking at what should be new for everyone. Although I may have touched on gas laws, but I don't think I did. So the next, so we're completely switching gears here now, and we're looking at what is really our first new topic of the course, and we're looking at gases and the gas laws. In terms of discovery and contribution of knowledge of chemistry, acids and bases contributed a lot. But most of what we know, most of the fundamental hypotheses that were generated hundreds, thousands of years ago came from studying gases, because gases are unique in the fact that they don't have a constant volume or a constant shape. Solids are boring. Solids, you can get to react, yes, but a rock is a rock. A piece of lead is a piece of lead. You can't really do much with it. Liquids are sort of fun. You can fill water balloons with them. They assume the shape of their containers, but nonetheless, their volume remains constant, and you can't compress them down, which is the entire science behind hydraulics. That's why your brakes work. That's why the jack works in your car and so forth. But gases, on the other hand, can be compressed. They don't have a definite volume. They don't have a definite shape. They assume the shape of their containers. They assume the volume of their containers. The only thing that might be finite about them is the quantity that you're working with if you're in a closed area. So there are four important measures of gases: pressure, volume, temperature, and quantity. And I've listed first for each of them the most important units that you'll use when you're working with gases, and then other units that you might be familiar with or that you might see as well. In terms of pressure, and you need to remind me to make sure I define pressure. In terms of pressure, atmospheres are the unit of choice. If you watch the Weather Channel or you check the weather each day, they are not going to report the air pressure in terms of atmospheres. But it is the most practical of the units that we'll use. When they report air pressure, what they're reporting is air pressure in terms of inches of mercury on the barometer. And inches are part of the English system. It's outdated. We shouldn't be using them. But again, it's what we're most familiar with. Like you're familiar with speed limit signs and miles per hour versus kilometers per hour. A day like today, the barometric pressure would probably be close to 30 or so inches of mercury. It's nice. It's fair. I don't see or predict a major weather change coming. But before that happens, you would detect a drop in air pressure. Millimeters of mercury is a little more practical. At least it uses metric units of millimeters. And then another unit that you're going to see is called the torr, T-O-R-R. Someone asked me last period if that there was a reason for that, or if it had an etymology, and it does. It was named after a scientist named Torricelli. To which I then said, I could be completely making that up for all you know. But there was, and it is. Volume is measured in liters, most practically, but it can be measured in any unit, preferably metric, that involves volume. And I went ahead and reminded you there that 1 milliliter and 1 cubic centimeter are equivalent units of volume. In terms of temperature, we want to carry out all calculations in units of Kelvin. The Kelvin scale of temperature is based on the Celsius scale of temperature. That is, one change in Kelvin is equivalent to a 1 degree change in Celsius. We don't say or read or write degrees Kelvin. You just write Kelvin. So a 5 degree change in Celsius would be equivalent to a 5 Kelvin temperature change. The Celsius scale is based on the freezing point and the boiling point of water. It was established that the freezing point of water was 0 degrees Celsius. The boiling point of water was 100 degrees Celsius. So they took those two temperatures, divided it equally into 100 parts, and that's what became a degree Celsius. And by default, again, that's what 1 Kelvin is. In other words, there are 100 kelvins in between the temperature at which water boils and water freezes. Degrees Fahrenheit is what you're most familiar with. Again, I can tell you that it's 78 degrees outside. You'd know right off the bat whether that's mild. You'd know what to wear. If I told you it was 25 degrees Celsius outside, you'd have to sit there and pull out your calculator or something to figure out what you needed to wear that day. I'm not too concerned with you being able to convert between Celsius and Fahrenheit. I gave you that formula sheet on the first day of class, and I'm pretty sure that it's on there. But you should have some familiarity with converting between the two units. And again, as I point these things out, you want to find them on that formula sheet so that later on you're not wasting time looking for it. You might be down to your last few minutes on the free response questions, or my test for that matter, and you don't want to be looking for that. And then the last important measure that's going to be involved in the formulas that you'll be using regards the quantity of gas molecules, and we measure quantity just like everything else, solids and liquids, in terms of numbers of moles. So again, make sure you know these four and know that they are interrelated. You can take a quantity of gas at a given temperature and volume, change the pressure, and it's going to affect the other measures. It won't change the quantity, but it will change the other measures. And we can relate all four of these which I'll do in a minute. But first, a few more things I wanted to point out about pressure. Any device that measures gas pressure is called a manometer. That's the general term for a device that measures gas pressure.
Did you say manometer?
Because this relationship. 0 Kelvin would be -273. 0 degrees Celsius, 273 Kelvin.
Sounds like professional.
And I think I have that. I'll get that. What do you call a device that measures air pressure? Barometer. What's all that? Now,
Jerry will love that.
another one of these, no one has yet to get it right questions. When you go to the doctor and get your blood pressure taken, what do they take it with?
Oh, it's the
That you know.
what's the start with? I got you.
Yeah, what did you say?
You don't got me if I have to.
I got mine yesterday, but I forgot.
It's a dot. No.
But I bet the person that did it didn't know what it was called.
Probably not. She didn't even know how to work it.
Definitely.
It goes around your head. What's it called? It starts with a D, don't it?
Does it start?
It's like it's DY something.
Diameter.
What'd you say?
It said carometer.
It's like diastolic.
Was he close?
What'd you say? Calorimeter? Is that what you were trying to say?
No, he was
That's
trying to
definitely
say,
wrong.
is it calorimeter?
No.
It's like a
What is it?
diastolic.
Okay, no one.
No.
I have no just started with those letters in the alphabet.
Oh, what?
I would have never had it.
So, the next time you go to the doctor,
What?
say, hey, nurse,
Hey, nerd.
whip that sphygmomanometer out and measure my blood pressure. Or, better yet, say, hey, do you even know what that's called? And she's going to say, what does it start with?
What if she's like sigmomedometer? Then what do you do? Then what do you do?
Are we going to
Just call up, like, coach, you know.
We will.
What pressure?
What pressure?
Nurse.
All right, now, I will give you a definition of pressure, but I want to show you first how air pressure was first measured, and again by Torricelli and Avogadro and some of these scientists from really close to 2,000 years ago. First of all, air pressure is established by all of the nitrogen and oxygen and CO2 and other gases that are in the air that are moving around us right now. And you don't realize it, but you're carrying, again, is exerted on us in all directions. Gas pressure, for that matter, exerts in all directions. You have, I assume at some point in time, blown up a balloon, and when you've blown it up and tied it off, you probably never noticed little gaps appear in the surface of that balloon. In other words, the air that you put in there stays in there and is moving so fast and strikes the walls of that balloon that it maintains the shape, the integrity of that balloon. Again, you don't sit there and look at it and see little dimples form in it. If you have, then you need to stop smoking whatever you So, air exerts pressure, which I still have yet to define, in all directions. And so, this is just a crude drawing of a barometer, which was one of the first manometers that was invented. So, air pressure, in addition to pushing in all directions, pushes down on the surface of, in this drawing, a container that holds mercury. As the air pressure pushes down on this mercury,
I wish I could. Yeah, I did like one time. I swear I'll have more.
I knew they
You want to check?
I will. I thought you were gonna be like, this is all there is, and like pour out like 5. Okay.
If I get some more, I promise I'll get
I just want
If I get any more,
I can't even listen like I can't even.
I can do it really loud, but I can't do that.
the video. Gosh, Joe. That's what you do right.
I feel like him. You know what's in the video?
Yeah.
I love when your hair is
And mercury is used because it's a very dense liquid. So it was evacuated of any gas and then inverted into, again, this pool or container of mercury. So mercury was used because it is very dense. So as the air pressure pushed down on the surface of this mercury, it caused the mercury to move up into this tube that, again, was otherwise empty of any gas, of any air, of anything. And the distance that it moved up the tube is what was recorded as the air pressure for that given day. And so if the mercury moved 760 millimeters above the surface of the pool of mercury, that's what the barometric pressure was recorded as. And someone asked in the other class, well, what happens if you moved that tube up and down? Well, as long as you didn't take the mouth of the tube out of the mercury, that level would stay at the exact same point, 760 millimeters above that mercury. And as air pressure changes, so if the air pressure were less that day, the mercury would not move up as far because the air pressure would be less. And that was the construct of the first barometer. All they did was measure how far up the air pressure pushed the volume of mercury. The size of the tube is irrelevant. The volume of mercury you had there in the bottom was irrelevant. As long as there was enough to rise up in the tube, it would always rise the same distance. What is that? Techno problem. Everything else I had written from the last class is now gone.
Are you a Boy Scout?
Volume, there's really not a whole lot to say about volume. Volume is volume. Volume is the space that a gas occupies, just like the space that a liquid or a solid would occupy. But gases do assume the volume of their container. So if you take a quantity of gas and put it in a smaller container, it's going to attain that volume. If you have a very small amount of gas in a very small container, but you open it in a room of this size, those gas molecules are going to spread out and occupy every available space in this room. So gases occupy the volume of the container that they are in. Temperature is probably the most important component of these measures of gas. And it's important that we begin now differentiating between temperature and heat, because in the last class I asked what is temperature, and the first thing that someone said was heat. Heat and temperature are two completely different concepts. Who remembers what the definition of temperature is? I know looking it up on your portable device doesn't count. It makes you a cheater. What?
Is it the total or average kinetic energy of the particles in a substance?
Yes. Temperature is a measure of the, if you take a sample of matter and you average the kinetic energy of all of the particles in that sample, that's the temperature. So it's the average kinetic energy of the particles in a sample. And what's the formula for kinetic energy?
E equals 1/2 mv squared.
1/2 mv squared, where m is, what's m?
Mass of the particle.
Mass, and v is velocity. So if we think about gas particles,
Physics.
gas particles have very little mass, which means they have to have what? A lot of speed, tremendous amount of velocity. That's why, again, when you're looking at a balloon, you don't see little dimples form. Those gas molecules are moving around in there so fast that even if you looked at it with a magnifying glass or a microscope, you would see those gas molecules essentially striking every square micrometer of the surface of that balloon every second. That's how fast they're moving. And that is what establishes pressure. It's the kinetic energy of gas molecules. It's their movement. So when you blow up a balloon, you're blowing in carbon dioxide and spit and whatever other stank breath you've got in the balloon, all of which are gases, and establishing a pressure. And it's the kinetic energy, the movement of those gas molecules, that maintain that pressure. So there is a direct relationship between temperature and pressure, because temperature is a measure of kinetic energy, and how much pressure is established is dependent on the temperature of the gas. What happens if you take a balloon and you put it in the refrigerator? It deflates some, it shrinks. And what's happening is you put it in the refrigerator or freezer and you start slowing down the movement of those gas molecules, and the gas pressure that was established at room temperature is now much less. But again, temperature and heat are two different ideas. They're two different concepts. We can measure heat conveniently by measuring temperature, but temperature itself involves the kinetic energy, the movement of the particles in a sample of matter. I've already said that for our purposes, ideally we want to use kelvins. Versus degrees Celsius, and definitely not degrees Fahrenheit. And we have to use kelvins because when we start looking at gas law formulas, if we use degrees Celsius, we can get, or we can have negative temperatures in degrees Celsius, and that could give us ultimately negative pressures and negative volumes, and that doesn't exist. There's no such thing as a negative volume or a negative pressure. So the Kelvin scale was developed so that you will always have either a 0 value or a positive value for temperature to plug into these formulas. And even though 20 or 30 minutes ago, I can't remember if I said this or not. The Celsius scale was set up based on the temperature at which water boils, which is 100 degrees Celsius, and the temperature at which water freezes, which is 0 degrees Celsius. So they took those two temperatures and they just divided it into 100 even marks, and each of those marks, each of those divisions then became a degree Celsius. All the Kelvin scale is the Celsius scale slit so that on the Kelvin scale, water freezes at 273 Kelvin and boils at 373 Kelvin. So again, a change in Kelvin is equivalent to a change in degrees Celsius. The reason they chose 273 as the magnitude that they slid the scale up is so that 0 on the Kelvin scale is what is called absolute 0. It is the temperature below which matter cannot get any colder. At absolute 0, kinetic energy equals 0. At absolute 0, even the motion of electrons in atoms comes to a stop. Kinetic energy equals 1/2 mv squared. You can't take away the mass, but you can lower the velocity of those particles to 0. It's never been done. In these multi-billion-dollar labs, they've taken matter down to within, I want to say, thousandths of a Kelvin, but have never been able to take it down to 0 Kelvin, to absolute 0. So absolute 0 on the Celsius scale is negative 273. It's actually negative 273.15, but we won't concern ourselves with the 0.15. When we looked at the stoichiometry problems involving gases, I told you that at standard temperature and pressure, 1 mole of any gas occupies a volume of what?
22.4.
22.4 liters. Doesn't matter what the identity of the gas is, if you have a mole of it and it's at standard temperature, and standard temperature is 0 degrees Celsius, and standard pressure is 1 atmosphere. And again, on a day like today where it's nice and there's not a change in weather coming, it's probably very close to 1 atmosphere out there right now, about 30 inches of mercury. Nice, clear day with no inherent change in weather coming. If you're given a problem where the conditions are not standard temperature and pressure, then you have to use one of the gas laws in order to calculate the volume. And the first of these that we're going to look at is called the ideal gas equation, or the ideal gas law. The ideal gas equation takes certain liberties, which I'll talk about later, but it allows us to relate pressure, volume, temperature, and moles of gas. The formula for it is PV equals nRT. And yes, it's on your formula sheet. If you have your formula sheet handy that I gave you on day 1, you'll see that there are actually 4 listed values for R, which is a constant. So if I gave you a problem and asked you to solve the pressure at a given volume, temperature, and gave you the number of moles of gas, which value of R would you use? No, I can't stand repeating myself.
Gas constant.
Right, which one?
Capital R. Oh, you 8.3.
4 listed there?
Yes.
Why that one?
Atmosphere. It has atmosphere.
Pressures measured in atmospheres.
Right, so solve the ideal gas equation for R, and you end up with PV over NT. And you should see a value listed there, 0.0821 liters, atmospheres, moles to the -1, which means it's in the denominator, kelvins to the -1. The order might be slightly different. But when, and again, this is one of those tricks of the trade. When you're faced with a problem like this, and you don't know which variable to use, solve it for the variable. It's going to give you the units that you need. You don't need the units that are involved in the other values for the gas constant. You need volume, pressure, number of moles, and temperature. Now, there are 5 problems over there on the board for homework. Those will be due Friday. For tomorrow, though, you are to write down what each of these laws relate and what assumptions must be made if you're going to use them. that will be due tomorrow. But I would suggest you go ahead and start working on these gas law problems because